Look up at the night sky. What do you see? A scattering of brilliant points of light, galaxies swirling like faint clouds, the familiar cosmic tapestry we've mapped for centuries. But what if I told you that everything we can see, every star and galaxy, might be just a fraction of the true story? What if the most important actors in the cosmic drama are not on the stage, but hidden in the wings, invisible to our most powerful instruments? Tonight, we are going on a journey into the deepest shadows of the cosmos to investigate one of the most profound and eerie possibilities in all of modern astronomy. We are hunting for dark stars. The very first moments after the Big Bang were a seething, chaotic soup of particles and energy. In that primordial darkness, before the first flicker of what we would call a normal star, the rules of the universe were being written. And according to a compelling theory, the first structures to form might not have been stars as we know them at all. Imagine, if you will, a celestial object so vast it could swallow our entire solar system without a trace. An entity that glows not with the fierce nuclear fire of hydrogen and helium, but with a far more exotic and mysterious power source, the annihilation of dark matter itself. These are the theoretical giants known as dark stars, and their existence would rewrite the first chapter of cosmic history. Finding them, however, is the ultimate challenge. By their very nature, they would be almost completely invisible, emitting little of the light our telescopes are built to capture. They could be lurking in the farthest reaches of space, or perhaps even closer than we think, masquerading as nothing, their immense gravity the only clue to their presence. This isn't just a story about hypothetical objects, it's a detective story on a universal scale. It's about piecing together clues from the earliest light in the universe, from the behavior of ghostly particles, and from the very structure of reality itself to answer a breathtaking question. Did the universe's first light come from a source we have yet to actually see? The journey to find these dark stars is a journey to understand the very foundations of everything, and it's a mystery we are only just beginning to solve. To understand how such a colossal object could even form, we need to rewind the cosmic clock to a time before the first stars ignited. The early universe was a much denser, hotter place, and it was filled with not just the familiar particles that make up you, me, and every star, but also with the enigmatic substance we call dark matter. Picture the cosmos about 200 million years after the Big Bang. Normal matter, the stuff that interacts with light, was spread out in a vast, relatively smooth fog. But dark matter, which feels gravity but not the other fundamental forces, had already begun to clump together under its own weight, forming vast, invisible structures known as dark matter halos. These halos acted as gravitational wells, drawing in the surrounding gas of hydrogen and helium. Now, in the story of a regular star, this infalling gas would compress, heat up, and eventually reach temperatures so extreme that nuclear fusion ignites in its core. But in these primordial halos, something different happened. The dark matter particles themselves, densely packed at the center of the halo, began to collide and annihilate one another. When a particle of dark matter meets its antimatter counterpart, they destroy each other, releasing a tremendous amount of energy in the form of heat. This dark matter annihilation produced a powerful, outward-pushing force, a kind of internal furnace that counteracted the gravitational compression. Instead of collapsing into a dense, fusion-powered star, the gigantic cloud of gas was puffed up and stabilized by this exotic energy source. The result was not a star in the conventional sense, but a vast, diffuse globe, a dark star. The scale of these objects is almost incomprehensible. While our Sun is a magnificent 1,000,000 kilometers across, a primordial dark star could have been up to 10 astronomical units wide. That means a single dark star could have stretched from our Sun all the way out to the orbit of Saturn. And its mass, instead of being just 1 times the mass of our Sun, they might have accumulated millions of times that amount. This immense size and the unique power source of dark matter annihilation would have made them glow with a faint, eerie light, primarily in the infrared spectrum, rather than the brilliant visible light of a fusion star. Their existence would have had a profound impact on the evolution of the entire cosmos. By heating the surrounding gas and delaying the formation of the first normal stars, these dark stars could have fundamentally altered the timeline of cosmic dawn. They might have provided the initial warmth that kept the early universe from collapsing back on itself too quickly, acting as the first great engines of structure in a dark and formless void. Finding evidence of these primordial giants would not just be about discovering a new type of object. It would be like finding the missing cornerstone of the universe's very first structures. But how does a perfectly smooth, featureless universe give birth to such intricate structure? The answer lies in the tiniest of imperfections. In the first fraction of a second after the Big Bang, the cosmos was not perfectly uniform. Quantum fluctuations, tiny ripples in the very fabric of spacetime, created minuscule variations in density. Think of it like a perfectly still pond into which a single grain of sand has been dropped. The ripples spread outward, creating regions of slightly higher and lower density. In the cosmic pond, these ripples were frozen into the expanding universe as it inflated at an unimaginable rate. These slight density differences were the seeds of everything to come. Dark matter, which makes up about 85% of all matter, was particularly sensitive to these fluctuations. Because dark matter doesn't interact with light or other electromagnetic forces, it isn't pushed around by radiation pressure. This meant that even the most minuscule overdensities in dark matter could begin to gravitationally attract more and more dark matter, growing steadily over hundreds of millions of years. These collapsing clouds of dark matter became the gravitational anchors, the skeletons upon which the first cosmic structures would be built. They drew in the surrounding primordial gas, which was almost entirely composed of the two simplest elements, hydrogen and helium, the raw leftovers from the Big Bang. This infalling gas, however, faced a dilemma. As it condensed, it should have heated up, leading to the birth of a normal, fusion-powered star. But within these dense, dark matter-rich cores, a different physical process took over. At the heart of these nascent structures, dark matter particles became trapped, whizzing around and colliding with one another. According to the leading theories, when certain types of dark matter particles meet, they can annihilate each other, converting their mass directly into energy. This annihilation process is incredibly efficient, releasing far more energy per particle than even hydrogen fusion. This created a powerful and steady heat source right at the center of the collapsing gas cloud. This outward pressure from the dark matter furnace acted as a perfect counterbalance to the relentless inward pull of gravity. Instead of collapsing into a tight, hot ball for nuclear fusion, the giant cloud of gas was stabilized, inflated to an immense size by this internal, exotic energy. It was a delicate dance between collapse and heat, resulting in an object that was not a star in the traditional sense, but something entirely new and colossal. This constant, immense energy source meant a dark star could shine for millions of years, not with the brilliant, short-lived fury of a fusion star, but with a steady, faint glow powered by the invisible matter at its core. The existence of these primordial dark stars isn't just a fascinating footnote in cosmic history. It might be the key to solving one of astronomy's most pressing modern mysteries. We now know that at the heart of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole. These cosmic monsters weigh in at millions, even billions of times the mass of our Sun. The real puzzle, however, is how they got so big so fast. We've observed fully formed supermassive black holes in the very early universe, at a time when, according to conventional models, there simply hadn't been enough time for them to grow from the collapse of a single massive star. It's like finding a skyscraper in the middle of a landscape where, by all accounts, only small huts should exist. So how do these giants appear almost instantly after the cosmic dawn? The answer might lie in the fate of the largest dark stars. Let's follow the life cycle of one of these immense dark objects, a supermassive dark star glowing with the heat of dark matter annihilation could have lived for millions of years. But its power source was not infinite. The dark matter at its core would have been gradually depleted as particles annihilated each other. Furthermore, as the normal gas cloud around it continued to evolve and stir, the dark matter density at the star's heart might have changed. Once the rate of dark matter annihilation could no longer sustain the tremendous outward pressure, the delicate balance would have been catastrophically broken. Without that internal furnace to hold it up, the entire structure, a gaseous sphere millions of times more massive than the Sun, would have experienced a direct and total gravitational collapse. This isn't the collapse of a single star into a stellar mass black hole. This is something on an entirely different scale. There would have been no supernova explosion, no violent shedding of outer layers. Instead, the entire colossal object would have fallen directly inward upon itself, a silent and swift descent into oblivion. In one swift cosmic event, a supermassive dark star could have transformed directly into a black hole of a similar immense mass. This direct collapse scenario provides a perfectly elegant solution to the early supermassive black hole problem. Instead of needing to start with a small black hole and slowly feed it for hundreds of millions of years, the universe could have created these behemoths ready-made in a single step. The supermassive black hole at the center of our own galaxy, Sagittarius A star, along with those we see in the most distant quasars, might not be the descendants of generations of merged stellar corpses. They could be the fossilized hearts of the universe's very first and most gigantic structures, the dark stars. This idea elegantly bridges two profound mysteries, suggesting that the invisible scaffolding of dark matter not only shaped the cosmos but also seeded it with the gravitational giants that govern it to this day. Now, let's turn our attention to a different, even more ghostly fate for some of these primordial giants. While many dark stars may have collapsed into the supermassive black holes at the centers of galaxies, not all of them would have had such a stable existence. The early universe was a violent and chaotic place, with proto-galaxies constantly colliding and merging. Within these turbulent environments, gravitational interactions were incredibly powerful, acting like cosmic slingshots. It is entirely plausible that during these chaotic dances, some dark stars could have been flung completely out of their host galaxies, cast adrift into the immense, empty darkness between galaxies. These would become rogue dark stars, the ultimate cosmic ghosts wandering the void for eternity. Think about the sheer isolation of such an object, a sphere of gas with the mass of millions of suns drifting in the profound blackness of intergalactic space. With no galaxy to call home, it would be utterly alone, separated from the nearest island of stars by millions of light years of nothingness. And because it emits almost no light, it would be completely invisible to our telescopes. We could be looking directly at one through our most powerful instruments and see absolutely nothing, a perfect void within the void. Its presence would only be betrayed by its gravity, but detecting the gravitational influence of a single, isolated object so far from any other mass is a challenge far beyond our current capabilities. It is a breathtaking concept, millions of solar masses of material, a potential fossil from the dawn of time, silently sailing through the cosmic abyss, completely unseen and unknown. The journey of such a rogue dark star would be a lonely one. Ejected from the bustling galactic environment where it was born, it would travel on an endless trajectory through the expanding universe. Over billions of years, its internal dark matter fuel would eventually run out. Without the energy from annihilation to support it, the star would face its final fate. But unlike its cousins that collapsed in the crowded galactic center, a rogue dark star's collapse would be a private, unobserved event. In the absolute silence of intergalactic space, the entire massive structure would implode, likely forming a monstrous black hole that would then continue its solitary journey through the void. This presents a fascinating possibility. Could the universe be peppered with isolated, primordial black holes, the graves of these rogue dark stars wandering unseen between the galaxies? Their existence would add a whole new layer of invisible mass to the cosmos, a population of dark, massive objects that could account for some of the mysterious dark matter we know must be there but cannot directly see. The hunt for these rogue giants may seem impossible, but their potential discovery would be one of the most significant in the history of astronomy, revealing a hidden chapter of cosmic evolution that played out in the darkest corners of space. So far, we've considered dark stars as colossal, solitary giants, but the cosmos has a preference for pairs, for cosmic dances between companions. What if the first structures weren't lonely monarchs, but instead existed in duos? Let's venture into the possibility of a dark star binary system, a pairing so strange it defies conventional observation. Picture two immense spheres of primordial gas, each one inflated to a size that dwarfs our solar system, each glowing faintly with the heat from their internal dark matter furnaces. They would orbit a common center of gravity, locked in a silent, graceful waltz. This would be a system with no blazing suns, no brilliant light to announce its presence. From our vantage point, it would appear as a patch of perfect, empty blackness. Yet within that void, an immense gravitational drama would be playing out. The dynamics of such a system would be governed purely by gravity, the most fundamental force in the universe. The two dark stars would exert a tremendous pull on each other, their orbits slowly decaying over millions of years as they lose energy. This loss of energy wouldn't be through friction or stellar winds, as in a normal binary system, but through the emission of something far more subtle and profound, gravitational waves. As any massive objects accelerate through space, they create ripples in the very fabric of spacetime itself, much like a spinning weight creates waves in water. For a binary system of objects as incredibly massive as dark stars, these ripples would be powerful indeed. Their orbital dance would send a continuous, low-frequency hum of gravitational waves echoing across the universe, a signature that, in theory, could be detected by future observatories. This presents a tantalizing method for finding these invisible giants. While our optical and radio telescopes would see nothing, a gravitational wave observatory capable of sensing the ultra-low frequencies produced by such slowly orbiting, supermassive objects might one day pick up their signal. It would be a whisper from the dawn of time, a direct detection of an invisible cosmic ballet. Furthermore, the gravitational influence of such a massive, compact binary system could also be detected indirectly. If it happened to lie along our line of sight to a more distant object like a galaxy or a quasar, its gravity would act as a lens, bending the light from the background source and creating multiple, distorted images or amplifying its brightness, a phenomenon known as gravitational lensing. Astronomers might observe a strange, unexplained lensing event that doesn't seem to correspond to any visible mass, a ghostly signature pointing to the presence of a dark star binary. The ultimate fate of such a system is as dramatic as its existence. As the two dark stars spiral closer and closer together over eons, their dance would become a frantic, final embrace. The loss of energy through gravitational waves would accelerate, pulling them into an inescapable merger. When they finally collided, the event would be one of the most energetic in the universe since the Big Bang, unleashing a cataclysmic burst of gravitational waves. This collision could trigger one of two incredible outcomes. The two dark stars might simply merge into a single, even more massive dark star, a behemoth that would continue its life until its dark matter fuel was spent. Or the violent merger could disrupt the delicate balance between dark matter heating and gravity, causing the combined object to undergo a direct and total collapse, instantly forming a single, supermassive black hole far more massive than any created by a single star. This binary pathway offers another elegant mechanism for creating the giant black holes we find at the hearts of galaxies, suggesting that the cosmic dawn might have been filled with the silent, invisible collisions of these primordial titans. This brings us to a pivotal question in cosmic history. What came before the very first normal stars? Astronomers refer to this first generation as population 3 stars, and they remain one of the great unsolved mysteries of the cosmos. We have strong theoretical reasons to believe they existed, but we have never directly observed one. They were behemoths thought to be hundreds of times more massive than our Sun, made purely from the pristine hydrogen and helium forged in the Big Bang. Their short, brilliant lives would have ended in spectacular supernova, seeding the universe with the first heavy elements, the carbon, oxygen, and iron that would later form planets and life. But how did these first giants themselves get their start? The formation process for such massive stars from a smooth cloud of gas is notoriously difficult for models to explain. This is where dark stars offer a revolutionary possibility. Perhaps population 3 stars did not form in isolation. Perhaps they were born from the ashes, or more accurately, from the cradles of their dark predecessors. The transition from a dark star to a normal star would have been a gradual cosmic handover. Let's envision a typical dark star shining steadily for millions of years thanks to its dark matter engine. Over its immense lifetime, it would have profoundly altered its local environment. Its faint but persistent infrared glow would have gently heated the surrounding primordial gas, and its sheer gravitational presence would have gathered vast reservoirs of hydrogen and helium around it. This dark star acts as a cosmic incubator, preparing the conditions for the next act. The critical moment arrives when the dark matter fuel at the star's core begins to dwindle. As the rate of annihilation slows, the outward pressure that once supported the star against its own gravity starts to weaken. The entire structure begins a slow, inexorable contraction. This isn't necessarily a catastrophic collapse straight into a black hole. For a dark star with a lower concentration of dark matter, or one situated in a region where dark matter is not as densely packed, the contraction could be more controlled. As the giant cloud of gas shrinks, it grows denser and hotter. But now, the chemical composition within it has been subtly prepared. The long period of stability provided by the dark star phase allowed the gas to become incredibly enriched with normal matter, perfectly poised for the next step. The temperature climbs, passing the threshold of 10 million degrees Kelvin, the point where hydrogen nuclei can overcome their mutual repulsion and begin to fuse together. In this scenario, the dark matter furnace doesn't just shut off, it hands the torch to nuclear fusion. The first flicker of a true stellar fire ignites within the heart of the collapsing dark star. What was once a diffuse, dark matter-powered globe transforms into a dense, raging inferno of nuclear fusion, a bona fide population 3 star. In this view, dark stars aren't an alternative to the first stars. They are their essential progenitors, the necessary nursery that allowed the first generation of true stars to grow to such tremendous sizes. Furthermore, the influence of dark stars on the first stars extends beyond a direct transformation. Even if a dark star ended its life by collapsing directly into a black hole, its legacy could have been the triggering of normal star formation all around it. The gravitational shock waves from such a colossal collapse would have rippled out through the surrounding gas clouds, compressing them and causing them to fragment. Imagine tossing a stone into a calm pond. The ripples spread out in all directions. The collapse of a dark star would send a much more powerful gravitational ripple through the cosmos. These waves of compression could have triggered the rapid collapse of nearby gas clouds, jump-starting the formation of multiple, smaller population 3 stars in a single dramatic event. This would solve another puzzle: how star formation began so efficiently and quickly in the early universe. Instead of a slow, gradual process, the death of one dark star could have given birth to an entire cluster of the first luminous stars. The most profound legacy of this progenitor relationship would be the chemical enrichment of the cosmos. Population 3 stars born from or triggered by dark stars would have lived fast and died young. Their tremendous mass meant they burned through their nuclear fuel in only a few million years before exploding as supernova. These titanic explosions were the universe's first factories for heavy elements. They forged elements like carbon, oxygen, neon, and iron in their cores and scattered them across space when they died. This metals pollution, as astronomers call all elements heavier than helium, was absolutely crucial for everything that followed. The second generation of stars, population 2, formed from gas that was already slightly enriched with these elements. This enrichment allowed gas clouds to cool more efficiently, leading to the formation of smaller, longer-lived stars like our Sun, stars stable enough to host planetary systems where life could potentially arise. Therefore, if dark stars were indeed the progenitors of population 3 stars, they would be the indirect architects of the entire chemical diversity we see in the universe today. They initiated the chain reaction that filled the cosmos with the raw materials for planets, oceans, and life itself, making them not just a fascinating theoretical idea, but a potential cornerstone of our own cosmic ancestry. While we've explored the dramatic births and deaths of dark stars in the early universe, there is another, even more haunting possibility. What if not all of these primordial giants met a fiery or collapsing end? What if some of them are still out there, having endured for almost the entire age of the universe? This is the concept of a relic dark star, a cosmic fossil that has somehow managed to survive for nearly 14 billion years. Imagine an object that witnessed the cosmic dawn, that glowed faintly during the era of the first true stars, and that has persisted silently through the formation of galaxies, including our own. These would not be the brilliantly inflated behemoths of the past, but something far more subtle. Ancient, cold embers lurking in the vast, dark outskirts of modern galaxies. The key to such incredible longevity lies in the delicate balance between their dark matter fuel supply and their immense mass. A dark star's lifespan is determined by how quickly it consumes the dark matter particles at its core through annihilation. For a relic to exist, this process must have been exceptionally slow. This could happen in a few ways. Perhaps the star formed in a region with a lower initial density of dark matter, giving it a less powerful but far more enduring engine. Or more intriguingly, the dark star might have evolved a clever mechanism to sustain itself. As it burned its initial central fuel, its immense gravity could have continuously drawn in fresh dark matter particles from the surrounding halo. If the rate of this replenishment nearly matched the rate of annihilation, the star could have maintained a stable, low-level glow for billions upon billions of years, a faint pilot light burning since the beginning of time. Finding such an object would be the ultimate challenge in observational astronomy. A relic dark star today would be a shadow of its former self. Having consumed most of its dark matter fuel, the outward pressure from annihilation would be minimal. Without that support, the star would have contracted significantly, becoming much denser and, crucially, much colder. It would no longer emit the faint infrared glow of its youth. Instead, its surface temperature might have plummeted to only a few tens of degrees above absolute zero. At such frigid temperatures, it would emit no visible light and only the most minuscule amount of long-wavelength radiation, making it virtually undetectable by conventional telescopes across almost the entire electromagnetic spectrum. It would be a cold, dark sphere of primordial hydrogen and helium, a ghost hiding in plain sight. So where would we even begin to look for such a perfect cosmic hideaway? The most promising hunting grounds are the extensive dark matter halos that envelop galaxies like our Milky Way. These halos are vast, diffuse spheres of invisible matter that extend far beyond the visible galactic disk. They are the perfect sanctuary for a relic dark star. Drifting in the immense, empty space of the galactic halo, such an object would be isolated, undisturbed, and incredibly difficult to spot. Its presence would only be betrayed by its gravity. One potential method of detection is gravitational microlensing. If a relic dark star were to pass directly between Earth and a distant, bright star, its gravitational field would act as a lens, bending the starlight and causing the background star to temporarily brighten in a very specific way. Astronomers already use this technique to detect rogue planets and brown dwarfs. A microlensing event caused by an object with the mass of millions of suns, but with no visible counterpart, would be a stunning anomaly, a powerful hint that something massive and completely dark is drifting through our galactic neighborhood. The implications of discovering a relic dark star would be monumental. It would be a direct, tangible messenger from the cosmic dawn, an object we could study to understand the conditions of the very early universe. By analyzing its properties, we could learn about the density and behavior of dark matter in the primordial cosmos. It would provide incontrovertible evidence for the entire dark star theory, confirming that these exotic objects were indeed a fundamental part of cosmic evolution. Furthermore, a relic could help solve the mystery of dark matter itself. By studying how it has interacted with and consumed dark matter over billions of years, we could gain unprecedented insights into the properties of these elusive particles. A relic dark star would be more than just a fossil. It would be a living laboratory for physics that we cannot recreate on Earth, offering a unique window into the nature of most of the matter in the universe. The hunt for these ancient embers is a search for a living piece of cosmic history, a silent witness to everything that has ever happened, waiting patiently in the darkness to tell its story. And now we arrive at one of the most mind-bending possibilities of all, the idea that life itself, against all odds, could find a way in the perpetual night surrounding a dark star. We are conditioned to think of a star's habitable zone, often called the Goldilocks zone, as a region bathed in sunlight, where the energy from a fusion reactor like our sun makes liquid water possible. But what if the life-giving warmth didn't come from light, but from something far more exotic? Imagine a planet orbiting a dark star. This world would be a place of absolute, unending darkness. No sunrise, no blue sky, no stars visible in the night because the night would be eternal. The only source of heat would be the faint, persistent infrared radiation emanating from the dark star's core, the byproduct of dark matter particles annihilating each other. In this profoundly alien system, the concept of a habitable zone still holds, but it would be defined purely by this infrared warmth. A planet orbiting at just the right distance would receive enough thermal energy to maintain surface temperatures that could allow for liquid water. This would not be a world of sun-drenched beaches and photosynthetic life. It would be a planet shrouded in a deep, global night, possibly enveloped by a thick atmosphere that traps what little heat it receives. The surface might be a global ocean kept liquid by the geothermal-like warmth from below, or a frozen ice shell with a subsurface ocean, much like Jupiter's moon Europa, but warmed by an external dark star instead of internal tidal forces. The very idea forces us to expand our definition of what makes an environment suitable for life, moving beyond the need for a bright, familiar sun. Consider the potential conditions on such a world. With no visible light, photosynthesis as we know it would be impossible. The base of the food chain couldn't be built on plants converting sunlight into energy. Instead, life would have to rely on chemosynthesis, drawing energy from chemical reactions, much like the bizarre ecosystems found around hydrothermal vents at the bottom of Earth's oceans. These deep-sea oases thrive in total darkness, supported by bacteria that metabolize chemicals like hydrogen sulfide. On a dark star planet, the energy source would be the persistent, low-level heat itself, potentially driving geological activity that could provide the necessary chemical soups. Life there might evolve to sense the world through sound, vibration, or even subtle differences in heat gradients, creating a biology utterly alien to anything we can imagine. The stability of such an environment is another fascinating aspect. A dark star powered by dark matter annihilation could offer a source of energy that is incredibly steady and long-lasting, potentially far more stable than the life cycle of a fusion star. Our Sun has a lifespan of about 10 billion years and will eventually become a red giant, destroying the inner planets. A dark star, depending on its dark matter supply, could shine with a constant warmth for tens of billions of years, perhaps even longer than the current age of the universe. This immense timescale would provide an extraordinarily stable platform for life to not only arise but to evolve and complexify over periods that dwarf the entire history of life on Earth. A civilization emerging on such a world would develop in perpetual darkness, their entire culture and technology built around a reality without light, their astronomy focused not on telescopes that see light, but on instruments that detect gravity, heat, and the faint whispers of particles. This leads to a profound and almost unsettling question. If such life exists, how would we ever find it? Our primary methods for detecting exoplanets rely on light, either the slight dimming of a star as a planet transits in front of it, or the wobble in a star's spectrum caused by a planet's gravity. A dark star system emits virtually no light, making these traditional techniques useless. Its planets would be doubly invisible. The only potential way to detect them might be through extremely sensitive infrared surveys that could pick up the faint thermal signature of a warm planet against the cold backdrop of space, or through the subtle gravitational lensing effect the entire dark star system would have on the light from more distant objects. The search for life around a dark star is for now a purely theoretical exercise, but it dramatically illustrates that the canvas for life in the universe might be far broader and stranger than we have ever dared to dream. It suggests that life could be hiding not only on distant Earth like worlds orbiting Sun like stars, but in the most absolute darkness imaginable, warmed by the ghostly glow of a physics we are only just beginning to understand. But what if a dark star's influence wasn't confined to its own immense structure? We've thought of them as passive consumers of dark matter, simply burning the fuel available in their immediate vicinity. Now consider a more active and dynamic role. Imagine a dark star not just as a campfire, but as a powerful gravitational pump, an engine that actively draws in dark matter from a vast region of space, altering the very fabric of its cosmic neighborhood. This is the concept of a dark matter fountain star, an entity whose hidden activity could leave a subtle, detectable fingerprint on the large-scale structure of a galaxy. The mechanism behind this is deeply rooted in gravity. A supermassive dark star is an object of incredible density and mass. Its gravitational pull is so powerful that it doesn't just attract the normal gas around it. It creates a deep, steep well in the fabric of space-time that dictates the motion of everything nearby, including the elusive particles of dark matter. While dark matter doesn't clump together like normal matter, its individual particles still follow curved paths through space, orbits dictated by gravity. A dark star would act as a massive anchor, causing dark matter particles from the surrounding halo to rain down upon it. As these particles fall inward, they gain speed, their orbits tightening around the star. This is where the fountain analogy becomes so compelling. While many particles would be captured and annihilated at the core, fueling the star's glow, the complex gravitational dance could also slingshot other particles away. Think of water flowing into a fountain's central pump. Some is sprayed outward in a beautiful, distributed pattern. Similarly, the intricate gravitational interactions near a dark star could fling some dark matter particles out on new, wider trajectories before they ever get a chance to annihilate. The dark star becomes a central hub, a chaotic crossroads where dark matter is both concentrated and redistributed. It actively processes the dark matter in its vicinity, pulling it in from the wider halo and ejecting a portion of it back out, effectively stirring the invisible component of the galaxy. Over millions of years, this continuous cycling could create a localized disturbance in the dark matter distribution, a kind of gravitational wake or density wave centered on the star. This leads to a fascinating possibility for detection. Astronomers map the distribution of dark matter in galaxies not by seeing it, but by observing its gravitational effects on the things we can see, primarily the orbital speeds of stars and gas. In a typical galaxy, the dark matter halo is modeled as a smooth, gradually decreasing cloud. But if a dark matter fountain star were present, it would create an anomaly in this smooth distribution. Its gravitational pumping action would create a localized overdensity of dark matter around itself, a dark matter hotspot. Conversely, the fountain effect might also create a slight underdensity, a drained region further out. These subtle irregularities would subtly influence the motion of visible stars and gas clouds in that part of the galaxy. An astronomer studying the rotation curve of a distant galaxy might notice a small but persistent kink, a deviation from the expected smooth curve that can't be explained by the visible mass alone. This wouldn't be the broad flattening of the curve that revealed dark matter's existence in the first place, but a smaller, sharper feature, a wiggle in the data. This wiggle would be the signature of a massive, invisible object dynamically interacting with the dark matter halo. It would point to a specific location in the galaxy and say, "Here lies something massive, something that is not a black hole or a cluster of stars, but an object that is gravitationally sculpting the dark matter itself." Finding such an anomaly would be like seeing the ripples on the surface of a pond and deducing that something is moving just beneath, out of sight. It offers a completely new, indirect method to hunt for these invisible giants by looking for the ghostly disturbances they create in the invisible sea of dark matter that permeates everything. One of the most powerful tools in an astronomer's kit is a trick of nature itself, a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. We know that massive objects warp the fabric of space-time, and as light travels through this curved space, its path bends. A massive object like a galaxy cluster can act like a cosmic magnifying glass, distorting and amplifying the light from more distant galaxies behind it. But what if the lens itself is completely invisible? This brings us to a detection method so clever it borders on poetic, using the universe's own optics to spot a dark star by the ghostly fingerprint it leaves on the light of others. Imagine a perfectly dark, massive sphere drifting silently through the interstellar void. From our perspective on Earth, it might one day pass directly in front of a distant, brilliant object like a quasar or a remote galaxy. We wouldn't see the dark star itself, it emits no light, but we would witness its profound gravitational influence. As the light from the background quasar travels toward us, it must pass through the warped space-time surrounding the dark star. This causes the light rays to bend around the object, converging at our telescopes from multiple paths. The result, instead of a single, point-like quasar, we might see multiple, distorted images of it, arranged in a perfect circle or arc around the central point of nothingness where the dark star resides. This effect, known as an Einstein ring, is a telltale signature of a massive compact object. If astronomers were to observe a perfect Einstein ring with no visible galaxy or star at its center to explain the lensing mass, it would be a compelling candidate for a dark star. The challenge, of course, is scale and probability. For a dark star to create a noticeable lensing effect, it needs to be both incredibly massive and relatively compact. A diffuse, inflated primordial dark star might be too large to create the sharp, focused ring we associate with strong lensing. However, a relic dark star that has contracted over billions of years, or the dense, dark matter-rich core of a more recent formation, could possess the required combination of high mass and small apparent size. Furthermore, the odds of a random alignment between a dark star, our telescope, and a bright background source are astronomically low. This is why the search would rely on large-scale sky surveys, like those conducted by the James Webb Space Telescope or the upcoming Vera-C. Rubin Observatory, which will continuously monitor vast swaths of the sky, cataloging millions of gravitational lensing events. Within that immense dataset, scientists will be searching for the anomalies, the inexplicable lenses that point to massive, invisible objects. There's another, more subtle form of this lensing that could be even more revealing: microlensing. While an Einstein ring requires a nearly perfect alignment, microlensing occurs more frequently when a foreground object passes in front of a single background star. As the dark star moves, its gravity briefly focuses the star's light, causing it to brighten in a very specific, predictable way over a period of days or weeks. The signature of this event is crucial. The duration and shape of the brightening curve tell us about the mass of the lensing object. A microlensing event caused by an object with the mass of 1,000,000 suns would have a distinctly different timescale than one caused by a lone planet or a brown dwarf. If a survey detected a microlensing event where the background star brightened as if magnified by a tremendous mass, yet no visible object could be found at the lens's location, it would be powerful, if not definitive, evidence for a dark star. We would essentially be seeing the shadow of the object cast not by blocking light, but by bending it. The true power of this method lies in its ability to probe the most elusive corners of the galaxy. A dark star acting as a gravitational lens doesn't need to be anywhere near us. It could be on the opposite side of the Milky Way or even in a nearby galaxy. As long as there is a bright source behind it and a powerful enough telescope to see the distortion, we have a chance to find it. This turns every distant quasar and galaxy into a potential backlight, illuminating the invisible structures that float in the foreground. It's a universal search strategy, allowing us to scan for dark stars across cosmic distances without them ever needing to emit a single photon of their own. The discovery of such a ghostly lens would not only confirm the existence of these exotic objects, but would immediately provide us with a precise measurement of its mass, offering a direct way to study the properties of something that has, until that very moment, existed only in theory. Now let's contemplate the final act of one of these cosmic giants. After shining for millions, perhaps billions of years, a dark star will eventually exhaust the dark matter fuel that sustained its immense structure. What remains is a colossal sphere of primordial hydrogen and helium, a relic of the early universe that has lost the internal engine holding it up against the crushing force of its own gravity. The fate of this object is not quiet. As the support fades, the entire structure begins to collapse inward. But this collapse might not always be a silent, direct plunge into a black hole. Under the right conditions, the demise of a dark star could give birth to something entirely new and strange, a dark star nebula. Picture the final moments. The dark matter annihilation rate drops below a critical threshold. The outward pressure vanishes and gravity takes full command. The outer layers of the giant star, a shell of gas millions of miles thick, begin to fall inward at a significant fraction of the speed of light. However, this infalling material doesn't simply disappear. In a dramatic and violent release of energy, the inner core's collapse could trigger a powerful rebound effect, a shockwave that ripples outward through the infalling layers. This shockwave could be so immense that it blows the star's outer envelope clean off, hurling it into the surrounding space at tremendous velocities. Instead of a complete collapse, the dark star experiences a titanic eruption, scattering its pristine, metal-free contents across light years. What would be left behind? At the center, the dense core would likely continue its collapse, forming a black hole, but surrounding it would be an expanding, shell-like cloud of gas, a nebula. Yet, this would be a nebula unlike any we've ever seen. A typical nebula, like the Orion Nebula, glows with brilliant colors because it is illuminated by the intense ultraviolet light from hot, young stars embedded within it. A dark star nebula would have no such central light source. The black hole remnant would emit no light, and the nebula itself would be made of pure hydrogen and helium, with no heavier elements to create complex emission lines. It would be a cosmic ghost, a vast, dark cloud of gas expanding silently into the void. So how could we possibly detect such a perfectly dark structure? Its presence would have to be inferred through its gravitational and dynamical effects on its environment. First, consider its gravity. A nebula containing the mass of millions of suns would exert a significant gravitational pull. If this dark nebula were to drift through a region of the interstellar medium populated with faint, visible gas clouds or background stars, its mass would distort their motions. Astronomers might observe a group of stars moving in an unusual, concerted way, as if being tugged by an invisible, extended mass. Alternatively, the expanding shell of the nebula itself would act like a colossal plow. As it pushes outward at high speed, it would sweep up the tenuous material of the interstellar medium, compressing it and potentially triggering the collapse of smaller gas clouds to form new, normal stars along its boundary. We might one day observe a strange, arc-shaped region of active star formation, a stellar nursery with no apparent trigger, its shape hinting at a powerful, invisible explosion that occurred long ago. The most tantalizing signature of a dark star nebula, however, might be its composition. Because the dark star was a primordial object, its ejected material would be the purest sample of the early universe imaginable, hydrogen and helium, entirely uncontaminated by the heavier elements forged in later generations of stars. If a future space telescope with incredibly sensitive spectrometers were to analyze the light from a distant quasar shining through such a nebula, the absorption lines in the quasar's spectrum would tell a remarkable story. They would show only the signatures of hydrogen and helium with a complete absence of any other elements. Finding such a pristine cloud in the modern universe would be like discovering a perfectly preserved fossil, a bubble of the infant cosmos that had somehow survived untouched for billions of years. It would be direct, physical evidence of an object that lived and died before the first metals even existed. The hunt for these dark nebulae is a search for the graves of the first giants, whose silent, expanding shrouds may still hold the secrets of the universe's earliest moments. Up until now, we've considered dark matter as a kind of exotic fuel, a substance that annihilates to produce heat. But what if the reality is far stranger? To venture into the next layer of this mystery, we need to push our imaginations into the quantum realm, where the rules that govern our everyday world break down and are replaced by a landscape of probability and connection. Let's explore a possibility so speculative it borders on science fiction: the quantum-coupled dark star. In this scenario, the dark matter particles at the heart of the star aren't just randomly colliding. They are deeply, fundamentally linked in ways that could create exotic states of matter and unleash energies beyond anything nuclear fusion could ever produce. The foundation of this idea rests on a quantum phenomenon known as entanglement. In the subatomic world, two particles can become entangled, meaning their properties, like spin or polarization, are linked in such a way that measuring one instantly influences the other, no matter how far apart they are. Albert Einstein famously called this spooky action at a distance, and it remains one of the most baffling and confirmed aspects of quantum mechanics. Now imagine a dark star with an immense density of a specific type of dark matter particle. Under these extreme conditions, could vast networks of these particles become quantumly entangled? Instead of individual particles annihilating in isolated events, you might have a coordinated, synchronized system. A change in one particle could ripple through the entire collective instantaneously, creating a unified quantum state across the star's core. This collective behavior could lead to the formation of something known as a Bose-Einstein condensate. In this exotic state of matter, individual particles lose their identity and merge into a single, coherent quantum entity, behaving like one giant wave rather than a collection of separate points. If the dark matter particles were bosons, a class of particles that can occupy the same quantum state, the core of a dark star could theoretically undergo this transition. The result would be a superfluid of dark matter, a substance with zero viscosity that flows without any friction whatsoever. This wouldn't just be a stable energy source, it would be a perfectly efficient one. The energy from annihilation events could be transmitted through this superfluid core with no loss, potentially leading to a much more stable and powerful output than in a disordered classical dark star. The entire core would act as a single quantum engine. The implications for energy release are even more staggering. In a normal dark star, energy is produced through random, pairwise collisions. But in a quantum-coupled system, an annihilation event might not be a simple one-to-one process. The entangled network could allow for a chain reaction, a cascade where the annihilation of one entangled pair triggers the annihilation of others linked to it across the vast core. This could result in a coordinated energy release of unimaginable scale, a quantum detonation rather than a steady burn. The power output could fluctuate in ways that defy our classical understanding of thermodynamics, potentially explaining unusual and periodic energy signatures that our models cannot currently account for. Furthermore, this deep quantum connection might allow the dark star to interact with the fabric of spacetime in entirely new ways. Some theories suggest that entangled particles are connected through microscopic wormholes or through a deeper layer of reality. If a significant portion of the universe's mass, in the form of a dark star's core, were in such a state, it could have subtle gravitational effects that go beyond what general relativity predicts. The star might create a unique kind of gravitational lensing, or its immense, coherent quantum nature could influence the very process of Hawking radiation around a black hole formed from its collapse. We would be looking at an object where the laws of quantum mechanics and gravity, the two pillars of modern physics that have so far resisted unification, are forced to interact on a macroscopic scale. Detecting such an object would require us to look for signatures that are, at present, purely theoretical. We might search for bursts of energy that have a distinct quantum signature, perhaps a specific pattern or frequency that suggests a coordinated rather than random release. The gravitational waves emitted from the merger of two quantum-coupled dark stars would carry a fingerprint of their internal structure, potentially showing harmonics and frequencies that are impossible for classical objects. While this remains a frontier of theoretical physics, it forces us to consider that the first structures in the universe might not have been governed by the simple rules we understand today. They could have been quantum computers on a stellar scale, their inner workings a complex dance of entanglement and coherence, hiding secrets about the fundamental nature of reality that we are only just beginning to grasp. Beyond the swirling arms of galaxies like our own, suspended in the vast galactic halo, float some of the oldest structures in the universe, globular clusters. These are ancient, densely packed spheres of stars, each containing hundreds of thousands, even millions of stellar inhabitants, all bound together by gravity. They are cosmic relics, having witnessed the formation of their parent galaxies billions of years ago. For a long time, astronomers believed they understood the simple, elegant dynamics of these clusters, that the combined mass of all their visible stars neatly explained how they moved. But recent, precise observations have revealed a gravitational puzzle at the heart of some of these clusters, a subtle anomaly that suggests there is more mass present than our telescopes can account for. This opens the door to a captivating possibility. Could a dark star, a fossil from the earliest epochs, be lurking at the very center of a globular cluster? To understand why this is such a compelling idea, we need to look at how stars behave within these dense systems. In a typical globular cluster, stars orbit the common center of mass, much like planets orbit the Sun, but in a complex, crowded gravitational dance. By carefully measuring the velocities of stars at different distances from the cluster's core, astronomers can map out the gravitational field and calculate the total mass required to keep the stars from flying apart. In many clusters, the numbers add up, but in a significant number of cases, there's a discrepancy. The stars, especially those near the very center, are moving faster than they should be if only the visible stars were pulling on them. There is an unseen source of gravity, a dark mass concentration, tugging on these ancient suns. This missing mass isn't enough to be an entire dark matter. Halo-globular clusters are generally thought to have lost their dark matter long ago. Instead, it points to a single, massive, and invisible object right at the cluster's heart. This is where the dark star theory offers an elegant solution. Imagine the early universe as a fledgling galaxy was just beginning to assemble. Within the vast dark matter halo of this proto-galaxy, smaller sub-halos would have also been collapsing. One of these smaller halos, exceptionally rich in dark matter, could have been the seed for what would eventually become a globular cluster. At its center, a supermassive dark star ignites, its exotic engine puffing it up to an immense size. This dark star acts as a gravitational anchor, pulling in the first population of normal stars that form around it. Over eons, as the cluster evolves, the dark star consumes its dark matter fuel. It may collapse directly into an intermediate mass black hole, an object with a mass thousands of times that of our Sun, which is exactly the kind of object that could explain the gravitational anomalies we see today. But there's another, even more intriguing possibility, that the dark star hasn't collapsed at all. What if it has persisted as a relic dark star, having somehow maintained a slow-burning dark matter furnace for nearly the entire age of the universe? Drifting within the protective density of the globular cluster, it could have found a sustainable equilibrium. Its immense mass, completely dark and invisible, would perfectly account for the unexpected gravitational pull on the surrounding stars. It would be a ghost at the feast, an unseen giant sitting at the center of a glittering ball of stars, its presence felt only by the way it orchestrates the motions of the stellar population around it. The environment of a globular cluster is actually an ideal hiding place for such an object. The dense core of a cluster is a dynamic environment where gravitational interactions can slingshot stars outward or pull them inward. This very process could work to the advantage of a relic dark star. As stars are flung around the core, their gravitational interactions could funnel fresh dark matter particles toward the central object, providing a trickle of fuel that has allowed it to survive for billions of years. It's a cosmic balancing act where the chaotic dance of the stars helps sustain the silent, dark heart of the cluster. Finding evidence for this would be a monumental challenge, but not an impossible one. Astronomers would look for several telltale signs. First, they would search for clusters that show a clear and concentrated mass anomaly in their cores, a gravitational signature that suggests a single, massive object rather than a distributed cloud of dark matter. Next, they could use the world's most powerful telescopes, like the James Webb, to search for any faint, unusual infrared emission coming from the precise center of such a cluster. While a relic dark star would be incredibly cold, it might still emit a whisper of heat that could, in theory, be detected against the cold background of space. The absence of any other plausible explanation, like a large cluster of neutron stars or white dwarfs that is too faint to see, would make the dark star hypothesis increasingly compelling. The discovery of a dark star within a globular cluster would be a breathtaking revelation. It would mean that these ancient stellar cities are not just simple collections of stars, but complex structures built around a primordial giant. It would directly connect the very first objects in the universe with some of the oldest structures we can observe today, providing a living bridge between the cosmic dawn and the present day. Furthermore, it would offer a unique natural laboratory. By studying how the stars move in the dark star's gravitational field, we could measure its mass with incredible precision. We could learn about the properties of dark matter by inferring how it has sustained this object for so long. A globular cluster dark star would be more than a solution to a gravitational mystery. It would be a window into the physics of the infant universe, preserved in a stellar time capsule that has been orbiting our galaxy since before the Earth even formed. Let's shift our perspective from the enduring giants to something far more fleeting and explosive. We've explored dark stars that shone for millions of years, but the cosmos loves variety. What if some of these objects were the ultimate cosmic ephemera, brilliant fireworks that flared with incredible intensity only to vanish almost as quickly as they appeared? This is the concept of the transient dark star, a celestial flash in the pan whose brief, dazzling life could easily be mistaken for a more familiar cataclysm. Imagine a region of space where the distribution of dark matter is not smooth and steady, but churned and turbulent. Perhaps due to the collision of two dark matter halos or the close passage of another massive object, a vast stream or a dense clump of dark matter is suddenly funneled directly into the core of a pre-existing gas cloud. This isn't a slow trickle of fuel, it's a massive injection like pouring gasoline onto smoldering embers. Within this nascent structure, the dark matter annihilation rate doesn't just increase gradually, it skyrockets. The sudden, enormous influx of particles leads to a runaway chain reaction of collisions and annihilations. The energy output, normally a steady hum, becomes a deafening roar. The internal furnace of the proto-dark star ignites with a violence it was never meant to sustain. This causes the entire gaseous structure to not just inflate, but to undergo a rapid, dramatic heating and expansion. For a short, spectacular period, this object could shine with a luminosity that rivals or even surpasses that of a small galaxy. Its light would not be the familiar spectrum of hydrogen fusion, but a unique signature dominated by the energy released from dark matter annihilation, potentially peaking in high-energy gamma rays. From our vantage point, this event would appear in our telescopes as a sudden, bright point of light where there was nothing before, a new transient in the sky. The challenge and the intrigue lies in interpreting such an event. Astronomers catalog numerous transient phenomena: supernova, gamma-ray bursts, tidal disruption events. Each has a distinct light curve, a specific pattern of how it brightens and fades over time. A transient dark star would have its own unique fingerprint. Unlike a supernova, which brightens over days or weeks as a shockwave tears through a star's outer layers, a dark star transient would likely ignite much more rapidly, its brightness soaring in a matter of hours as the dark matter fuel is consumed in a frenzied burst. And its fade would be different too. Once the sudden influx of dark matter is exhausted, the annihilation rate would plummet. Without the sustained outward pressure, the entire structure could collapse back in on itself almost as quickly as it brightened, causing the light to vanish not with a slow decay but a relatively swift dimming. It would be a brilliant, short-lived flare, a beacon of exotic physics that appears and disappears on a timescale that defies the life cycle of normal stars. This opens up a fascinating possibility. Could some of the unexplained transients already recorded in astronomical surveys actually be the signatures of these dark star flashes? When a new point of light appears and doesn't perfectly match the profile of a known event, it's categorized as an unusual or peculiar transient. Among these oddities, there may be hidden the evidence we seek. The key to identification would be multi-messenger astronomy correlating the light with other signals. A dark matter annihilation event would be expected to produce a specific ratio of gamma rays to other particles like neutrinos. If a bright optical transient were detected simultaneously with a burst of high-energy neutrinos coming from the same direction, and if the light curve didn't match any known stellar explosion, it would point strongly towards an exotic source like a transient dark star. We would be witnessing the death throes of an object that never lived a long life, a brilliant final confession of its dark matter heart. The existence of such fleeting giants would add a whole new layer of dynamism to the early universe. It suggests that the cosmic dawn wasn't just a gradual brightening from the first steady stars, but was also punctuated by these sudden, brilliant flares, brief, violent eruptions that momentarily illuminated the primordial darkness before sinking back into oblivion. They would have acted as powerful but short-lived engines, heating their surroundings and potentially triggering waves of star formation in their vicinity before their own light had even faded. The hunt for them is a search for ghosts within the data, for anomalies that challenge our classification schemes and point the way to a more complex and wondrous cosmic history. Now, let's consider a force that shapes the cosmos on every scale, from the smallest particles to the largest galaxies: magnetism. We are familiar with the magnetic fields of planets like Earth, which shield us from solar radiation, and with the immense fields generated by the swirling plasma of stars and the turbulent gas within galaxies. But what if one of the most powerful magnetic engines in the universe has been hiding in plain sight, or rather, in perfect darkness? The unique internal dynamics of a dark star could theoretically generate magnetic fields of a scale and strength that defy imagination, creating invisible forces capable of reaching across interstellar space. To understand how, we need to picture the heart of a dark star not as a simple, homogeneous ball of gas, but as a dynamic, churning system. The energy released from dark matter annihilation would heat the surrounding hydrogen and helium, creating powerful convection currents. Imagine a pot of water boiling on a stove. Hot plasma from the core would rise toward the surface, cool, and then sink back down, creating a continuous, turbulent circulation. In any electrically conductive fluid like this ionized plasma, such motion can generate a magnetic field through a process known as a dynamo. It's the same basic principle that gives Earth and the Sun their magnetic fields, but the potential scale within a dark star is utterly different. The critical factor is the sheer size and mass of these objects. A supermassive dark star contains an ocean of plasma millions of times more massive than our Sun, all undergoing this convective motion. Furthermore, the rotation of the star itself would twist and shear these plasma flows, stretching and amplifying magnetic field lines in a feedback loop that could create a field of staggering power. We are not talking about a field slightly stronger than a sunspot. We are talking about a magnetic field that could be billions, even trillions of times stronger than the Sun's average field, potentially rivaling the fields found around magnetars, the most magnetic known objects in the universe, but on a vastly larger physical scale. Such an immense magnetic field would not be confined to the dark star. It would extend outwards for light years, creating a vast, invisible magnetosphere around the object. This magnetic influence could have profound effects on the dark star's evolution and its local environment. For instance, it could channel and focus the outgoing radiation and particles from the annihilation processes, creating powerful jets erupting from its magnetic poles, similar to the jets seen from quasars and pulsars, but powered by an entirely different engine. These jets, invisible in optical light but potentially detectable in radio or X-rays, could transport energy and momentum far into the surrounding primordial gas, influencing how and where the first normal stars would eventually form. Perhaps the most tantalizing aspect of this idea is that it offers a potential new method for detection. While the dark star itself would be dark, its incredibly powerful magnetic field would interact with the cosmic rays that constantly zip through the galaxy. Cosmic rays are high-energy particles, mostly protons and atomic nuclei traveling at near light speed. When these charged particles encounter a strong magnetic field, their paths are bent and twisted. A dark star with a gargantuan magnetic field would act as a powerful cosmic ray deflector, creating a kind of shadow or a zone of lower cosmic ray density downstream from it. If astronomers could map the distribution of cosmic rays across the sky with extreme precision, they might find an unexplained hole or a dip in the flux, a quiet patch in the constant cosmic rain. This shadow would point directly to the location of a massive, invisible object with an intense magnetic field, a signature that fits a dark star perfectly. This magnetic footprint could also solve another puzzle: the origins of the highest energy cosmic rays, particles with energies millions of times greater than those produced in our largest particle accelerators, remain one of astronomy's great mysteries. Could a dark star's magnetic field act as a natural particle accelerator? The field's immense strength and scale could potentially slingshot charged particles to unimaginable energies, making these invisible giants a candidate source for the most energetic particles in the universe. Finding an ultra-high-energy cosmic ray event that seems to originate from a patch of empty space could therefore be a clue that we are looking at the location of a dark star. Its magnetic influence, stretching across light years, would be the ghostly hand that guides and accelerates these particles on their journey through the cosmos. The search for these magnetic ghosts adds a fascinating new dimension to the hunt, suggesting that we might find them not by the light they emit, but by the invisible, powerful force they exert on the particles that fill the void. But what if the dark matter fueling these giants is not a single, simple substance? Our discussion so far has treated dark matter as a uniform entity, but many physicists suspect the invisible sector of the universe could be just as rich and diverse as the visible one. This leads us to a fascinating and complex possibility: the multi-species dark star. Imagine that dark matter is not one but several different types of particles, each with its own unique properties, much like the familiar family of particles that make up atoms. In such a scenario, a dark star would become a far more intricate and layered cosmic engine, with an internal structure and life cycle dictated by a delicate interplay between these different dark matter species. At its heart, this idea transforms the dark star from a simple furnace into a complex chemical plant. Instead of a single type of particle annihilating in a straightforward reaction, you could have multiple processes occurring simultaneously. Some dark matter particles might annihilate directly with their own antiparticles, producing a burst of energy and specific secondary particles. Others might undergo more complex interactions, perhaps decaying into lighter particles first, which then go on to annihilate. Each of these pathways is known as an annihilation channel, and each channel would release energy at a different rate and produce a distinct signature of gamma rays, neutrinos, or other exotic particles. The total energy output of the star would then be a complex sum of all these different channels operating in concert. The internal structure of such a star could become stratified, much like the layers of an onion. Heavier dark matter particles, feeling a stronger gravitational pull, might sink towards the very center of the star, creating a dense core where their specific annihilation processes dominate. Lighter, more mobile dark matter particles might be distributed throughout a larger volume, creating a surrounding shell where a different type of energy production occurs. This layered engine would have profound consequences for the star's stability and lifespan. The rate at which the dark matter fuel is consumed would no longer be a simple calculation. It would depend on the relative abundances of each particle type and how efficiently they can find each other to annihilate within the star's vast interior. This complexity directly ties the fate of a dark star to the specific model of dark matter that nature has chosen. For instance, if dark matter includes a particle that interacts with itself via a powerful force, similar to the strong nuclear force that binds atomic nuclei, it could form dark matter nuclei or even dark atoms within the star's core. These composite structures could alter the annihilation rate dramatically, potentially leading to periods of stable, steady energy output punctuated by occasional, violent bursts if the dark matter ignites in a new way. The star's lifespan could be significantly extended or shortened based on the precise mix of particles involved. A model with a rapidly annihilating particle might lead to short-lived, brilliant dark stars, while a model dominated by a more sluggish particle could allow for the ancient relic dark stars we discussed earlier. The most exciting implication for astronomers is that this multi-species model would give a dark star a unique, detectable fingerprint. The cocktail of particles annihilating within it would produce a specific spectrum of high-energy radiation. Our telescopes, like the Fermi Gamma-Ray Space Telescope, are constantly scanning the sky for gamma-ray signatures that cannot be explained by known astrophysical sources. A dark star powered by multiple annihilation channels might emit a combination of gamma rays at very specific energies, a complex barcode that, if detected, would not only confirm the existence of dark stars but would immediately tell us exactly what dark matter is made of. It would be a direct glimpse into the physics of the invisible universe, decoded from the light of a cosmic giant. The search for these multi-species dark stars is therefore not just a hunt for a new astronomical object. It is a fundamental test of our deepest theories about the nature of most of the matter in the cosmos. This concept transforms a dark star from a mere consumer of dark matter into a potential production facility, a cosmic engine that could be actively shaping the very substance that powers it. To grasp this, we need to consider the leading candidate for dark matter, weakly interacting massive particles, or WIMP. The prevailing theory suggests that in the hot, dense early universe, WIMP were created in abundance. As the cosmos expanded and cooled, their numbers dwindled, leaving behind a relic density that forms the dark matter halos we infer today. But within the extreme environment of a dark star, this process could be thrown into reverse, turning the star into a natural WIMP factory. The engine for this production is the immense energy released by dark matter annihilation itself. When two WIMP collide and annihilate, they don't just disappear. According to Einstein's famous equation, their mass is converted into pure energy, which typically manifests as a burst of gamma rays or other standard particles. However, in the seething heart of a dark star, where these annihilation events are occurring at a furious rate, that released energy is so concentrated that it can spontaneously create new pairs of particles from the vacuum of space. This is a fundamental principle of quantum mechanics. Energy and matter are interchangeable. If the energy from an annihilation event is high enough, it can condense back into a particle and its antimatter counterpart. In this case, the most likely particles to be created would be the same WIMP that just annihilated. The dark star's core becomes a self-sustaining cycle. WIMP annihilate, releasing energy that then creates new WIMP, which are then gravitationally trapped and ready to annihilate again. This cycle would have a dramatic effect on the local environment. Instead of simply depleting the dark matter in its core, a dark star could actually maintain a much higher density of WIMP than the surrounding halo. It acts as a gravitational trap, pulling in dark matter from its vicinity, and its internal factory mechanism ensures a steady replenishment. The result could be a self-regulating system, a steady-state equilibrium where the rate of WIMP production nearly matches the rate of annihilation. This would give the dark star an incredibly long and stable lifespan, potentially allowing it to shine for billions of years. The star isn't just burning a finite fuel tank, it's cultivating a dense, thriving population of dark matter particles within its own heart. For astronomers, this factory function opens up a novel and exciting avenue for indirect detection. If a dark star is indeed producing WIMP, some of those particles will inevitably escape its gravitational grasp, streaming out into the surrounding space. This would create a localized overdensity of dark matter, a kind of diffuse halo or a wind emanating from the star. We could then search for the telltale signs of these escaping WIMP. When WIMP annihilate, they produce a specific signature of gamma-ray photons at very particular energies. If a future gamma-ray telescope were to scan a region of space and find an unexpected, point-like source of this specific annihilation radiation, and if that source had no visible counterpart, no star, no galaxy, no nebula, it would be a powerful indicator that we are looking at a dark star WIMP factory. The star would be betraying its presence not by the light it emits, but by the unique fingerprint of the invisible particles it is constantly producing and expelling. Furthermore, the dense cloud of WIMP surrounding a factory star could interact with other cosmic phenomena in detectable ways. If a stream of normal cosmic rays, high-energy protons and atomic nuclei were to pass through this dark matter cloud, the WIMP could subtly alter their paths or even absorb some of their energy, creating a faint shadow or a distortion in the cosmic ray background that we could, in theory, map. The existence of such a dark star would not just be a solitary discovery, it would provide a natural laboratory for studying the properties of WIMP themselves. By analyzing the spectrum of the gamma rays from the annihilation products, we could measure the mass of the WIMP particle and understand how it interacts with itself. A dark star, in this view, becomes more than a theoretical object. It becomes a key that could unlock the fundamental physics of the majority of the matter in our universe. While the vast spiral galaxies like our own Milky Way offer a bustling cosmic metropolis to search within, sometimes the most profound discoveries are made not in the bright city centers, but in the quiet, dark countryside of the cosmos. For the hunt for dark stars, the most promising hunting grounds may not be the grand spirals, but their smaller, quieter cousins, the dwarf galaxies. These faint, diffuse collections of stars are more than just miniature versions of larger galaxies. They are cosmic relics, pristine environments that have remained relatively unchanged for billions of years, and they could hold the key to isolating the gravitational signature of a single, invisible giant. The power of a dwarf galaxy as a dark star detector lies in its simplicity. A massive spiral galaxy is a complex gravitational ecosystem. Its total mass is a convoluted sum of billions of stars, enormous clouds of gas, and a vast, dominating dark matter halo. Trying to pinpoint the subtle gravitational tug of one additional massive object within that bustling chaos is like trying to hear a single whisper in a roaring stadium. A dwarf galaxy, by contrast, is a much quieter room. It contains far fewer stars, less gas, and its overall gravitational field is less complicated. If a dark star is hiding within a dwarf galaxy, its immense mass would represent a much larger fraction of the system's total gravity. Its influence would not be a faint whisper lost in the noise. It would be a pronounced voice, significantly altering the motions of the few stars that are there. Furthermore, dwarf galaxies are notoriously dominated by dark matter. In fact, some of the faintest dwarf galaxies are thought to be composed of over 99% dark matter, with the visible stars representing just a tiny tracer population floating in a massive sea of invisible mass. This might seem counterintuitive. Wouldn't a dark star be harder to find in a place already flooded with dark matter? The crucial distinction is between a smooth distribution and a point source. The general dark matter halo of a dwarf galaxy is spread out over a large volume, creating a broad, gentle gravitational slope. A dark star, however, would be an incredibly concentrated knot of mass, a point-like gravitational anchor. Its presence would create a sharp, steep well in the galaxy's gravitational landscape, a distinct anomaly that would cause the stars nearest to it to move with unexpectedly high velocities. Astronomers can map this gravitational landscape by carefully measuring the speeds of individual stars within a dwarf galaxy. In a simple system without a central dark star, the stellar velocities would follow a predictable pattern, gradually decreasing as you move outward from the center. But if a massive dark star resides at the core, stars orbiting near it would be whipped around at much higher speeds than the overall dark matter halo would dictate. It would be like watching a handful of bees buzzing furiously around an invisible hive. By tracking these stellar motions with powerful telescopes, researchers can create a detailed map of the mass distribution, and a pronounced, localized spike in the center would be a smoking gun. The recent discoveries of ultra-faint dwarf galaxies orbiting the Milky Way have made this search more feasible than ever. These are among the most dark matter-dominated objects known in the universe, often containing only a few thousand stars. Their simplicity makes them perfect laboratories. If a dark star exists in one of these systems, its gravitational influence could be so dominant that it might even cause the entire dwarf galaxy to wobble slightly as it orbits the Milky Way. The search is already underway, with astronomers analyzing data from surveys like the Gaia spacecraft, which precisely tracks the motion of billions of stars, looking for any tiny, unexplained gravitational perturbations within these faint galactic satellites. Finding a dark star in a dwarf galaxy would be a discovery of monumental importance. It would confirm that these objects aren't just theoretical curiosities from the early universe, but that they can form and persist in a variety of environments. It would provide a pristine, relatively simple system in which to study the properties of a dark star without the complicating factors of a busy galactic center. By measuring its mass and its effect on the dwarf galaxy, we could finally move from theory to direct evidence, turning a compelling idea into an observed reality and opening a new window into the hidden architecture of the cosmos. Now, let's consider a dark star not as a static object, but as a dynamic, breathing entity. Every star, even our own sun, has a natural rhythm, a subtle pulse or oscillation caused by waves rippling through its interior. For a normal star, these vibrations are like a faint, constant hum, influenced by convection and rotation. But for a dark star, this internal music could become a powerful, resonant symphony, with consequences that might make it detectable across the cosmos. This leads us to the idea of a resonant dark star, an object whose very heartbeat is synchronized with the exotic engine at its core. The key to this phenomenon lies in a fundamental principle of physics: resonance. Think of pushing a child on a swing. If you give a small push at just the right moment, at the peak of the swing's arc, you add a little energy each time, and the swing goes higher and higher. That perfect timing is resonance. Now, imagine the entire structure of a dark star is like that gigantic swing, naturally oscillating in and out, expanding and contracting over a period of days or years. Meanwhile, deep in its core, the dark matter annihilation engine is releasing a steady flow of energy. Normally, these two processes, the star's pulse and its power source, are independent. But what if they became linked? Under specific conditions, the rate at which dark matter particles annihilate could enter into a perfect synchrony with the star's own gravitational oscillations. Perhaps a contraction of the star squeezes the dark matter particles closer together, dramatically increasing the rate of collisions and annihilations. This sudden burst of energy then pushes the star back outward, causing it to expand. As it expands, the dark matter density drops, the annihilation rate falls, and gravity takes over again, pulling the star back inward to start the cycle anew. This creates a self-sustaining feedback loop, a resonant cycle where the dark matter furnace doesn't just burn steadily, but pulses in a regular, predictable rhythm. The effects of this resonance could be dramatic. Instead of a faint, constant glow, a resonant dark star could exhibit periodic bursts of brightness. It would become a cosmic lighthouse, not flashing with visible light, but with pulses of infrared radiation or even gamma rays, its output rising and falling in a clear, repeating pattern. This periodicity would be its most distinctive feature, a fingerprint that separates it from any other known astronomical object. A supernova brightens and fades once, a pulsar flashes due to rapid rotation. But the pulse of a resonant dark star would be tied to the fundamental oscillation of its entire structure, a much slower and more profound heartbeat driven by the dance between dark matter and gravity. This regular pulsation would do more than just make the star brighter at times. It could actually stabilize the object over immense timescales. A normal dark star might face a gradual decay or a catastrophic collapse as its fuel depletes. But a resonant dark star locked in this efficient cycle could find a perfect balance. The periodic bursts of energy would prevent the gravitational collapse from going too far, while the natural oscillation would prevent the energy output from running out of control. It could settle into a stable, long-term pulsation that allows it to survive for billions of years, a rhythmic giant humming quietly in the dark. For astronomers, this predictability is a gift. Searching for a perfectly dark object is like looking for a black cat in a dark room. But searching for a dark object that emits a regular, repeating signal is an entirely different challenge. We could scan the sky with infrared and gamma-ray telescopes, not just for steady sources, but for any that blink on and off with a consistent period. The timing of these pulses would be a direct probe of the dark star's internal structure. The period of oscillation tells us about its average density and mass, much like the pitch of a bell tells you about its size and composition. By analyzing this unique signal, we could effectively weigh the dark star and understand its internal dynamics without ever seeing it directly. The hunt for a resonant dark star becomes a search for a specific cosmic rhythm, a telltale beat that could reveal the presence of one of the universe's most mysterious giants. To truly grasp the potential influence of these dark giants, we must revisit the universe in its infancy, a time often called the cosmic dark ages. After the brilliant flash of the Big Bang faded, the expanding cosmos cooled sufficiently for protons and electrons to combine, forming neutral hydrogen atoms. This event, known as recombination, left the universe filled with a thick, pervasive fog of this neutral gas. For hundreds of millions of years, this fog rendered the cosmos opaque to ultraviolet light. Space was a dark, featureless void. The end of this era, the epoch of reionization, was one of the most transformative periods in cosmic history, when the first sources of light began to blast away the fog, burning ionized bubbles into the neutral hydrogen and ultimately making the universe transparent. The identity of these first cosmic lighthouse keepers has long been a subject of intense debate. Were they the first population of massive, fusion-powered stars, or could dark stars have played a pivotal and perhaps dominant role? The key lies in the type of radiation required to rip electrons away from hydrogen atoms. This process, called ionization, demands high-energy ultraviolet photons. Now consider a standard population 3-star, a behemoth hundreds of times the mass of our Sun. It would have blazed with a fierce, hot blue light, producing a tremendous amount of ionizing UV radiation. For decades, these stars have been the leading candidates for driving reionization, but a supermassive dark star presents a fascinating and powerful alternative. While its overall glow is faint and primarily in the infrared due to its relatively cool, inflated surface, the physics of its dark matter engine suggests it could have been an incredibly efficient ultraviolet producer. The annihilation of dark matter particles doesn't just release heat. It can create a cascade of high-energy particles, including a flood of ultraviolet photons deep within the star's core. Unlike a fusion star where energy is generated in a central core and must slowly fight its way to the surface, the energy in a dark star is produced throughout its vast volume via annihilation. This could allow a significant portion of that energetic UV radiation to escape directly into space. The impact of a single, supermassive dark star on its surroundings would have been profound. Imagine one of these million solar mass giants, a sphere larger than our entire solar system, shining not with visible light but pumping out a steady, intense stream of ionizing UV radiation. It would act less like a lantern and more like a cosmic ultraviolet laser, carving out a massive ionized bubble in the neutral hydrogen fog around it. The scale of this bubble could have dwarfed those created by the earliest clusters of normal stars, because a dark star could form earlier and live much longer than a short-lived population 3-star. Its ionizing influence would be both immense and persistent. It wouldn't just flicker on and off in a few million years. It could maintain its ionizing output for tens of millions of years, constantly expanding its transparent zone and pre-processing the cosmic medium for the stars that would follow. This sustained bombardment would have fundamentally altered the environment in which the first galaxies began to assemble. This leads to a crucial question about the timeline of cosmic dawn. Observations from telescopes like the James Webb Space Telescope are now peering back into this epoch, and they are finding that reionization may have occurred earlier and more efficiently than some models predict. If the first sources of light were only the massive but short-lived population 3 stars, it's challenging to explain how the entire universe became transparent so quickly. Dark stars offer an elegant solution to this puzzle. As the first luminous structures to form, they would have gotten a head start on the reionization process. While the first fusion stars were still struggling to ignite within their gaseous cocoons, dark stars could have already been shining, their UV radiation beginning to eat away at the neutral hydrogen on a colossal scale. They would have served as the pioneers of transparency, creating vast, interconnected bubbles of ionized gas that allowed the light from subsequent generations of stars to travel farther and more freely. The very nature of the radiation from a dark star could also leave a distinct signature that future observatories might detect. The spectrum of light from a dark star, the specific balance of different wavelengths from infrared to ultraviolet, would be unique, shaped by its dark matter power source rather than nuclear fusion. As this light traveled through the early universe, it would have imprinted a specific pattern on the cosmic microwave background, the faint afterglow of the Big Bang. While this signal would be incredibly subtle, next-generation space telescopes designed to study the polarization of this background radiation might one day find an anomaly, a faint whisper of a non-thermal source that points to the presence of these exotic objects. Furthermore, the pattern of how reionization proceeded across the cosmos, whether it was a slow, uniform process or a patchy one dominated by a few brilliant sources, could hold the key. If the data reveals that reionization was driven by a relatively small number of incredibly powerful and long-lived engines, it would strongly favor the dark star hypothesis over a model reliant on countless short-lived fusion stars. Ultimately, the question of what ended the cosmic dark ages is not just about identifying a light source. It's about understanding the transition from a simple, neutral universe to the complex, transparent, and structured cosmos we see today. Dark stars force us to reconsider this foundational chapter. They may not have been the brilliant beacons we typically imagine, but their ghostly ultraviolet glow could have been the primary chisel that sculpted the first windows into the universe, allowing the light of subsequent stars and galaxies to finally shine through. Theirs would be a legacy written not in visible starlight, but in the very transparency of space itself, a fundamental and invisible contribution to the cosmic landscape we now observe. But if we venture beyond the familiar territory of WIMP, the landscape of dark matter candidates opens up into even stranger possibilities. One of the most compelling alternatives is a hypothetical particle known as the action. Imagine a dark matter particle that is not massive and weakly interacting, but instead is incredibly light and behaves more like a wave than a discrete speck of matter. Actions were originally proposed to solve a completely different, deep puzzle in particle physics concerning the symmetry of the strong nuclear force. But they have since emerged as a perfect candidate for dark matter. Their properties would give rise to a type of dark star so exotic, it would challenge our very definition of what a star can be. An action dark star wouldn't be powered by the violent annihilation of particles, but by a far more subtle and elegant process, a collective transformation. The core mechanism of an action dark star hinges on a quantum phenomenon called the Primakov effect. In the presence of a strong magnetic field, actions can spontaneously convert into photons, particles of light. Now picture the heart of a dark star, a vast sphere rich with these action particles. They wouldn't be colliding and exploding. Instead, they would form a coherent, wave-like field, oscillating with a specific universal frequency. If this action field exists within a region with a powerful magnetic field, perhaps generated by the churning plasma of the star itself, as we discussed earlier, then this conversion process can begin. The actions en masse would slowly and steadily transform into photons. This is not an explosive chain reaction, but a continuous, quiet trickle of light being born from darkness. The energy source is the mass of the action field itself, being converted directly into electromagnetic radiation with impeccable efficiency. This fundamental difference in power source leads to a star with characteristics utterly distinct from a WIMP-powered giant. A WIMP dark star glows with a broad, thermal spectrum of infrared heat, the result of random collisions and the subsequent heating of gas. An action dark star, however, would emit light of a very specific single wavelength. Because all actions of a given type oscillate at the same precise frequency, the photons they produce would all have identical energy and therefore identical color. Instead of a faint, warm glow across a range of infrared light, an action star would shine like a perfectly tuned laser, emitting a monochromatic beam of radio waves or microwaves. This is arguably one of the most unique and detectable signatures any astronomical object could possibly have. We wouldn't be searching for a faint smudge of heat. We would be listening for a pure, steady tone emanating from the darkness. The potential observability of such a signal makes the hunt for action dark stars a particularly exciting frontier. Our most powerful radio telescopes are designed to scan the skies for specific frequencies. If theorists can narrow down the possible mass range for the action particle, astronomers can then tune their telescopes to the corresponding frequency and systematically search the sky for a point source that shouldn't be there. It would be like scanning through the static of a radio, searching for one perfectly clear, unwavering note that signifies the presence of a hidden giant. This search is already underway in a different context, with experiments looking for actions converting to photons in laboratory magnetic fields. Finding an action dark star in space would be the ultimate validation, a natural experiment on a colossal scale. The structure of an action dark star would also be profoundly different. Without the need for a dense core of annihilating particles to provide outward pressure, an action star could be even more diffuse than a WIMP star. It might resemble a gigantic, tenuous cloud of gas whose shape is maintained not by thermal pressure from within, but by the gentle, continuous push of the monochromatic light it generates. Some theories even suggest that action stars could exist without any normal matter at all, being purely condensed clouds of the action field itself, glowing softly from their own internal conversion process. These would be the most minimal stars imaginable, entities of pure dark matter that have learned to sing their own faint song into the void. The discovery of such an object would not only revolutionize astronomy, but would finally illuminate the true nature of the invisible substance that holds the universe together. But perhaps the most dramatic fate awaiting these invisible giants is not a solitary collapse, but a spectacular collision in the void. We've already considered the silent waltz of a dark star binary system, but what happens when that dance reaches its inevitable, breathtaking finale? The merger of two supermassive dark stars would be one of the most energetic events conceivable in the universe, a cataclysm that would momentarily outshine entire galaxies, not with light, but with a storm of ripples in the fabric of space-time itself. Envision the final moments of this cosmic ballet, two colossal spheres of primordial gas, each millions of times the mass of our Sun, and inflated to a size that could engulf our entire solar system, have spent eons spiraling ever closer. Their mutual gravitational pull acts as an inescapable cord drawing them together. As they approach, their immense gravity begins to distort their forms, stretching them from perfect spheres into teardrop shapes. The final orbits become a frantic, accelerating plunge. In the last few seconds, they slam into each other at a significant fraction of the speed of light. The collision is not a simple merging of two clouds. It is a violent, chaotic upheaval that releases a truly staggering amount of energy. However, the vast majority of this energy would not escape as a flash of light, but in a form that is invisible to our eyes, a powerful, transient burst of gravitational waves. This is where our most advanced listening posts for the cosmos come into play. Observatories like LIGO and Virgo are exquisitely tuned to detect these ripples in spacetime. They have successfully recorded the mergers of black holes and neutron stars, events that typically last for a few seconds and produce a characteristic chirp, a rapid increase in the frequency and amplitude of the waves as the objects spiral inward. A dark star merger, however, would produce a signal unlike any other. The key difference lies in the nature of the objects involved. Black holes and neutron stars are incredibly compact. They are essentially points of immense mass with no internal structure that gravitational waves can probe. When they merge, it's a clean, sharp event. Dark stars, by contrast, are vast, diffuse, and messy. They are not points but enormous, gassy bodies. This fundamental difference would be written into the gravitational wave signal. Instead of a clean chirp, the merger of two dark stars would produce a much more complex and prolonged waveform. The initial in-spiral would be similar, but the moment of collision would be drawn out. The two gaseous bodies wouldn't simply merge and form a black hole instantly. They would splash together, their outer layers mixing and sloshing in a turbulent, chaotic process that could last for minutes or even hours. This prolonged interaction would imprint a unique signature on the gravitational waves, a complex pattern of frequencies and harmonics that would tell the story of the internal structure of the stars themselves. It would be the difference between hearing two solid rocks clacking together and two giant water balloons splattering against each other. The sound reveals the nature of the colliding objects. Furthermore, the aftermath of such a merger holds another fascinating possibility. The combined object, a single, even more massive dark star, might not immediately collapse. The tremendous energy of the collision could violently stir and mix the dark matter concentrated at the cores of both stars, potentially reigniting the annihilation furnace to an even greater intensity. This could lead to a brilliant, temporary flare across the electromagnetic spectrum, from infrared to gamma rays, a fleeting beacon signaling the violent birth of a new dark supergiant. Alternatively, the merger could deliver the final, destabilizing blow, causing the new object to undergo a direct collapse into a supermassive black hole in a second, even more energetic gravitational wave burst. For astronomers, catching both the gravitational wave signal and a corresponding electromagnetic flash would be the holy grail, providing a multi-messenger confirmation of these theoretical giants and unlocking secrets about their internal composition and the nature of dark matter itself. The silent, invisible collision of these primordial titans would, for a brief moment, scream its existence across the cosmos in a language of gravity that we are only just learning to understand. Yet we must ask a profound question about the very heart of our own cosmic home, the Milky Way. For decades, we have accepted that a single, supermassive black hole named Sagittarius, a star, sits at our galactic center, its immense gravity dictating the motions of billions of stars. But what if our interpretation of that gravitational anchor is incomplete? What if, instead of a solitary Leviathan, the galactic core hosts an entire swarm of smaller, invisible giants, a dense collection of dark stars whose combined mass and gravitational pull perfectly mimic the effects of a single, colossal black hole? This radical idea, known as the dark star swarm hypothesis, could elegantly resolve several persistent puzzles about the strange dynamics we observe in the universe's most crowded neighborhoods. To understand why this idea is so compelling, picture the environment at the center of a large galaxy. It is a place of unimaginable density, with stars packed together thousands of times more tightly than in our quiet suburban spiral arm. In such a chaotic stellar metropolis, the gravitational influences are incredibly complex. Our primary evidence for a supermassive black hole is the observed orbits of stars very close to the center, which whip around at astonishing speeds, implying a single, incredibly massive and compact object is holding them in its grip. However, a dense swarm of dark stars could produce an almost identical gravitational signature. If you had 1 million solar masses worth of dark stars orbiting each other in a region just a few times larger than our solar system, their combined gravity would create a steep, central potential well that would force nearby stars to trace those same rapid, tight orbits. From a distance, it would be nearly impossible to distinguish this collective pull from that of a single point-like mass. This swarm scenario offers a fresh perspective on one of the most puzzling aspects of galactic centers, the relative quietness of our own Sagittarius A star. While it is undeniably massive, it is a far less active and energetic engine than the supermassive black holes powering distant quasars. If it were a single, true black hole, we might expect it to be accreting more material and shining more brightly as it consumes the abundant gas and stars in its vicinity. A dark star swarm, however, provides a natural explanation for this calm demeanor. Instead of a voracious singularity with an event horizon from which nothing can escape, the galactic center would be filled with massive, gaseous objects. Infalling matter would not vanish forever. It would collide with the dark stars, creating complex, turbulent interactions that dissipate energy in a less efficient, more subdued manner than the violent disk of accretion around a black hole. The relative quiet of our galactic heart might be a sign that it is not an empty pit, but a teeming, invisible city. Furthermore, the swarm model could account for the mysterious objects known as G-sources, which have been observed orbiting near Sagittarius A star. These are strange, dust-enshrouded entities that look like gas clouds but somehow survive their close approaches to the central mass without being completely torn apart by tidal forces, as a cloud would be near a black hole. If the central mass were a swarm, the tidal forces experienced by a passing object would be distributed across the entire volume of the swarm, rather than being focused on a single, infinitely dense point. This would be a far gentler, though still intense, environment, potentially allowing these resilient structures to survive their perilous journeys. Their strange durability is a clue that the central gravitational field might be more complex and extended than a simple black hole model suggests. The formation of such a swarm also presents a fascinating narrative. In the early history of the Milky Way, the galactic center would have been the ultimate dark matter nexus, the deepest gravitational well where dark matter particles would have accumulated in incredible densities. This would have been the perfect birthplace not for one, but for hundreds or even thousands of primordial dark stars. They could have formed in a gigantic cluster, a stellar nursery of invisible giants. Over billions of years, gravitational interactions would have caused them to sink even closer to the exact center, merging and interacting, eventually settling into a densely packed, dynamically relaxed swarm. What we call Sagittarius A star would not be a single object, but the entire, vibrant ecosystem of these ancient dark stars, their collective presence the true ruler of the galaxy. This same principle applies to the universe itself, but on a scale that is almost impossible to comprehend. Every star, planet, and nebula we see today is built from elements forged in the fiery hearts of previous generations of stars. Our own sun, the Earth, and even our bodies are made of this cosmic recycling stardust enriched with carbon, oxygen, iron, and all the other elements that make complex chemistry and life itself possible. But this presents a fundamental challenge for astronomers. How do we study the universe in its original, pristine state before this cycle of stellar life and death began? The answer may lie in finding an object that somehow skipped this entire process, a relic that has remained untouched and unchanged. This is the profound power of a dark star. It acts as a perfect cosmic time capsule, sealed during the universe's infancy and preserving its original ingredients for billions of years. To understand why this preservation is so unique, we need to consider what a dark star is made of. Unlike every other object we have ever observed, from the most distant galaxy to the nearest brown dwarf, a dark star would be composed of nothing but hydrogen and helium. These two elements were the only products of the Big Bang, the raw materials from which the first everything had to form. A dark star, born from a collapsing cloud of this primordial gas and powered by an exotic dark matter engine, would have no internal mechanism to create heavier elements. Its power source is annihilation, not fusion. It never reaches the incredible temperatures and pressures necessary to fuse hydrogen into helium, let alone forge carbon or oxygen. It is a static chemical snapshot, a bubble of the infant cosmos that was never polluted by the metallic ash of later stellar generations. The value of such a pristine sample to science cannot be overstated. If we could somehow analyze the composition of a dark star, its spectrum would be breathtakingly simple. It would show the unmistakable absorption lines of hydrogen and helium, and absolutely nothing else. There would be no faint traces of lithium, no signature of carbon, no evidence of the elements that we now know are essential for planets and life. Finding this perfect simplicity in the modern universe would be like an archaeologist discovering a perfectly sealed tomb from an ancient civilization, its contents untouched by time, offering an unblemished view of a lost era. For cosmologists, it would be the ultimate calibration point, a baseline confirming our models of Big Bang nucleosynthesis, the process that created the first elements with direct physical evidence. Furthermore, the internal structure of a dark star would also preserve the physical conditions of the early cosmos, because it is inflated by its dark matter furnace rather than compressed by fusion. The gas within it remains relatively diffuse. This means the laws of physics operate within it in a way that is much closer to the conditions of the smooth, post-Big Bang universe than to the extreme environments inside modern stars. Studying its stability, its oscillations, and its overall behavior would give us insights into the fundamental constants and processes that govern the cosmos when it was only a few 100 million years old. It would be a living fossil not just in its composition, but in its very physical state. The hunt for these time capsules is therefore a hunt for the most direct evidence of our cosmic origins. While we can look far out into space with telescopes like the James Webb and see back in time to early galaxies, what we are seeing is still light that has been processed through stars and gas that have already been enriched. Even the most distant, ancient galaxies show signs of heavy elements, meaning the cycle of star birth and death had already begun. A dark star, by contrast, would predate all of that. It would be a primary source, a witness to the era before the first supernova ever lit up the darkness. Discovering one would allow us to study the universe not as it was reflected in later objects, but as it truly was in its simplest, most elemental form. It would be the closest we could ever come to taking a physical sample from the cosmic dawn, offering a clear, uncontaminated window into a time before complexity, and revealing the humble, two-element beginnings from which our entire rich and varied universe eventually emerged. Now let's push our thought experiment to its most speculative and thrilling extreme. We've considered dark stars as natural phenomena, as cosmic fossils, and even as potential cradles for life. But what if a dark star were not just a natural wonder, but a technological one? What if an intelligence far more advanced than our own encountered one of these invisible giants and saw not just a celestial object but an unparalleled opportunity? Imagine a civilization so advanced that it could somehow harness the very fabric of reality, turning a dark star into the ultimate power source for a project of unimaginable scale. This is the concept of the technosignature dark star, a construct so vast and perfectly engineered that its signature would not be a beacon of light, but a ghostly fingerprint etched into gravity and thermodynamics. The very idea forces us to reconsider the Kardashev scale, the framework we use to classify civilizations by their energy consumption. A Type 2 civilization, for example, is one that can harness the entire energy output of its star, perhaps by building a Dyson sphere around it. Our Sun produces a staggering amount of energy, but it is nothing compared to the potential output of a supermassive dark star. Its power source, the steady annihilation of dark matter, could be millions of times more efficient and long-lasting than hydrogen fusion. For a civilization capable of such an engineering feat, a dark star would be the ultimate prize. A Dyson sphere around our Sun would capture visible light. A megastructure around a dark star would have to be designed for an entirely different purpose to capture something we cannot see: the immense heat generated by the annihilation process deep within the star. What would such a structure even look like? It would be the most paradoxical construct imaginable. Since the dark star emits almost no light, the megastructure wouldn't need to be reflective or deal with intense radiation pressure. Instead, it would be a vast, dark engine designed for maximum thermodynamic efficiency. Perhaps it would be a colossal sphere, not of shining solar panels, but of hyper-advanced metamaterials that absorb the dark star's faint infrared glow and convert it directly into usable energy. Or maybe it would be something more intricate, a network of conduits or filaments that somehow tap directly into the dark matter annihilation reactions at the star's core, a technology that manipulates the dark sector itself. This would not be a structure built for illumination, but for pure, concentrated power generation on a galactic scale. The detection of such an artifact, however, presents the ultimate challenge for our astronomers. We couldn't search for it with optical telescopes. By design, it would be completely invisible across the entire electromagnetic spectrum. Its builders would have mastered stealth on a cosmic level. But there are two potential ways this perfect invisibility might fail, leaving behind a subtle, unnatural signature. The first is waste heat. The second law of thermodynamics is unforgiving. No process, no matter how advanced, can be 100% efficient. Some energy must always be lost as waste heat. Even if this civilization captured 99.9% of the dark star's energy output, the remaining 0.1%, wasted and radiating away as infrared light, would be enormous. From our vantage point, we might observe a mysterious, point-like source of infrared radiation that seems to have no natural explanation, a warm spot in the cold darkness that doesn't correspond to any known type of star, nebula, or galaxy. It would be the thermal exhaust of an engine of godlike proportions. The second, and perhaps more telling, signature would be gravitational. A megastructure massive enough to encapsulate or harness a dark star would itself have a significant gravitational pull. The motion of the dark star and any visible objects near it would be subtly influenced by the presence of this immense, invisible shell. We might detect a strange, precise regularity in the orbits of nearby stars or gas clouds, a pattern that suggests an artificial mass distribution rather than a natural one. Furthermore, if the advanced society were using the captured energy for propulsion or other large-scale activities, the resulting gravitational waves, the ripples in space-time from moving massive objects, could carry an unnatural, non-random pattern. Our gravitational wave observatories might one day detect a signal that isn't the chirp of a black hole merger or the steady hum of a binary system, but a complex, structured waveform that hints at directed, intelligent activity. This thought experiment does more than just fuel our imagination. It reframes our entire search for extraterrestrial intelligence. For decades, we have scanned the skies for radio signals and laser pulses, looking for a message in a bottle. But a civilization capable of engineering a dark star would be so far beyond our own that its most obvious signature might not be a deliberate signal, but the unintended byproduct of its cosmic scale existence. They might not be trying to communicate at all. We would simply be witnessing the aftermath of their ambition, like ants discovering a hydroelectric dam. The search for such a technosignature forces us to look for anomalies in the most fundamental aspects of physics, in the distribution of heat and the curvature of space. It suggests that the greatest evidence for other minds in the universe might not be a flashing light, but a silent, perfectly dark monument to power, whose shadow we can only detect by the way it bends the universe around it. So we arrive at the final contemplation for these cosmic giants. What becomes of a dark star at the end of its life? The answer is not a single destiny, but a branching path of possibilities, each more profound than the last, and each deeply tied to the nature of the dark matter that gives it life. The ultimate fate of a dark star is a story written by the balance between its internal furnace and the relentless pull of gravity. The most straightforward end is a quiet fading. For a dark star with a limited supply of dark matter fuel, the end comes not with a bang but with a whimper. As the last particles annihilate in its core, the steady outward pressure that has supported its immense structure for millions of years finally ceases. Without this internal support, the entire gaseous sphere begins a slow, inexorable gravitational contraction. It doesn't explode, it simply shrinks, growing denser and colder over millennia. Its faint infrared glow, the last remnant of its exotic power, dwindles until it vanishes entirely. What remains is a cold, dark sphere of primordial hydrogen and helium, a ghost of its former self, drifting silently through the galactic void. This relic could persist for eternity as a perfectly dark, massive object, a monument to a bygone era, its presence detectable only by the faintest gravitational tug on the fabric of space-time around it. But for many dark stars, the end is far more dramatic, a direct and total collapse into a black hole. This is the fate most likely for the true supermassive dark stars, the ones that accumulated millions of solar masses of material. When their dark matter fuel is depleted, the collapse is not slow and gentle. It is catastrophic. The entire structure, a sphere larger than our solar system, falls inward upon itself. There is no supernova, no violent expulsion of outer layers. The collapse is silent and swift, a swift descent into a gravitational point of no return. In one decisive cosmic event, the dark star ceases to exist, and in its place, a black hole of equivalent, immense mass is born. This direct collapse scenario is one of the most elegant solutions to the mystery of how supermassive black holes appeared so early in the universe's history. The giants at the centers of galaxies may not have grown slowly. They may have been born fully formed from the demise of their dark star predecessors. There is, however, a third, more transformative path. What if the dark matter depletion is not total, but instead allows for a handover to a more familiar power source? As a dark star contracts, the temperature and density of its hydrogen and helium core rise dramatically. It's conceivable that before a total collapse into a black hole can occur, the conditions might become ripe for the ignition of nuclear fusion. In this scenario, the dark star does not die but is reborn. The exotic dark matter engine sputters out, only for the fierce fire of hydrogen fusion to ignite in its heart. The immense, diffuse dark star would then transform into a supermassive normal star, a population 3 giant blazing with intense ultraviolet light and beginning a new, though short-lived, chapter powered by conventional stellar physics. Its death would then come in a spectacular supernova, seeding the cosmos with the first heavy elements. This would make the dark star a cosmic chrysalis, a necessary precursor that gives birth to the first true light in the universe. Yet our imagination must stretch even further to consider fates we have yet to conceive. The physics of dark matter is still a frontier of science. What if certain types of dark matter can decay or transform in ways that trigger a phase transition within the star? Could the cessation of annihilation unleash a different, unknown form of energy? Perhaps the collapse itself, under these extreme and unique conditions, doesn't form a standard black hole, but something even stranger, like a boson star or a gravastar, theoretical objects that challenge our understanding of singularities. The final act of a dark star might involve a spectacular release of energy in a form we cannot currently predict, a flash of gravitational waves or a burst of particles that would rewrite the laws of physics as we know them. No matter which path it takes, a dark star leaves a permanent imprint on the cosmos. If it collapses into a black hole, it seeds the universe with the gravitational giants that will govern galaxy formation for eons. If it triggers the birth of the first stars, it initiates the chemical enrichment that makes planets and life possible. Even if it simply fades away, it remains as a hidden reservoir of primordial matter, a time capsule from the universe's first moments. The legacy of a dark star is woven into the very fabric of the cosmos, a silent, foundational force that shaped everything that came after. Their story reminds us that the universe's greatest dramas may have been played out not in the brilliant light of stars, but in the profound and creative darkness that preceded them. And so, our journey through the shadows comes to a close, but the story of dark stars is far from over. We have ventured from the very first moments after the Big Bang, where these colossal giants may have been the universe's inaugural structures, to the silent, drifting relics that could be hiding in the halos of galaxies today. We've considered their roles as progenitors of the first true stars, as the possible seeds for the supermassive black holes that baffle us, and even as potential, albeit profoundly alien, cradles for life in the eternal night. The sheer diversity of these theoretical objects is staggering, from the steady burning primordial behemoths to the fleeting transient flashes, from the resonant, pulsing giants to the quantum-coupled engines that defy our current physics. Each possibility opens a new window into the cosmos, suggesting that the invisible fabric of the universe is woven with far more complexity and wonder than we have ever seen. The implications of discovering just one dark star would be nothing short of revolutionary. It would be a direct confirmation of a foundational chapter in cosmic history, proving that the first light did not come from the sources we expect. It would provide incontrovertible evidence for the existence and nature of dark matter itself, finally allowing us to study the properties of the particles that make up most of the universe's mass. Our understanding of galaxy formation, the origins of supermassive black holes, and the entire timeline of the cosmic dawn would have to be rewritten. A dark star would be more than a new class of object. It would be a master key, unlocking multiple doors in astrophysics simultaneously, from the smallest particles to the largest structures. This search is a testament to human curiosity. We are no longer limited to mapping the cosmos by the light it emits. We are learning to see with the eyes of gravity, to listen for the whispers of gravitational waves, and to sense the faintest thermal signatures against the cold backdrop of space. The hunt for dark stars is driven by the same instinct that has always propelled science forward, the refusal to accept that what we see is all there is. It is a recognition that the universe's greatest secrets are often kept in the darkest corners, waiting for a clever mind and a new tool to bring them into the light. The dark secrets of the universe are not meant to remain hidden forever. They are an invitation, a challenge to look deeper, to think bigger, and to question our most fundamental assumptions. So the next time you gaze up at the night sky, remember that the empty spaces between the stars are not truly empty. They may be filled with giants, with ghosts, with the invisible architects of everything we see. Stay curious, for the next great discovery might not be a new point of light, but the profound and thrilling signature of the darkness itself.